So 8.1, I mean 8.1 is just boundary condition. 8.2 is starting to derive the equation, which is more important, but then a little bit more math. So the starting point is just like what we did last time. Start with the four equations with the Maxwell equation without source. So basically, it's inside. So you have a cylindrical waveguide. You have the z direction is the invariant direction, meaning the cross section is the same along z, right? And now you just write down the four Maxwell equation again. So you have well, E is partial minus partial B partial T, but this everything is proportionate E to the minus T, right? So that becomes I omega T, right? And so divergence D is 0, but Jackson in here is using E, is assuming basically you have a constant, a uniform mu and epsilon. So originally its divergence D is 0, right? But for a uniform epsilon, so D is epsilon E, so you can pull the epsilon out, and right hand side is 0, so divergence is. It doesn't matter if you want to more general, you can keep the D field, but for this section, Jackson just use the E field. Right. Likewise, the Ampere's law originally is partial D becomes minus I omega D. But then again, now you use epsilon here, then this becomes E. And there's no J, no free current density. Okay, and then but then Jackson also used the H as B over mu, change that to B, and then multiply mu over the others. Okay, so that's Ampere's law, and divergence B is 0 is always true. Okay, so that you have four equations. This, and that. Okay, so we do that, but then we want to separate the derivatives into along the z direction and the perpendicular direction. So you have this z direction. The perpendicular direction is basically any direction perpendicular to the z direction. So you can say it's x and y direction, but Jackson, you just combine them and call it t direction. A 10, what do you call it? Transverse direction. This is a transverse direction. Okay, and the wave equation, of course, we already derived that, like in section 7, we already derived the wave equation from this set of equations. The equation is minus omega squared epsilon mu, and operate on either E and B, you know. All the components of E and B satisfy this a plus. This is a plus, yeah. This is equation 8.17. This is the wave equation. Okay, and so we divide that in section 7, which very easy. Just take another curl of that and use the vector identity. That's one curl B is this one. So you combine, use the vector identity and show that this is true. Okay, but for waveguide, we want to separate the z direction and t direction for both the derivative and the field. Like E, but the field you can separate E is E transverse which is a vector because it has two components. And then the z component, you can say the component is easy, but then it's in the direction. And likewise, d plus b sub c in the z direction. Okay. And then the gradient also, gradient is equals to gradient t plus z partial. Right. That's we want to separate that and then write down the equation relating the E and B. So basically, the maximum equation will rewrite it in two components, T and Z, and then later on we'll derive an equation that is, I mean, basically it's the same as this one. Very trivial, just separate the Z derivative in the Laplacian. That we can write it down later. But, first, we'll work on the Maxwell equation. Write everything in separate into T and Z. Okay, and now we can start using. I think 8.3 involve I think this and that. So we can work on that. Right. For this one, so we have T plus C plus C. Basically, just separate these things into different components. And the right-hand side is also two components. Okay, so after we separate the two components, obviously there will be two equations, one involved in the transverse direction, the other in the z direction. Right, and that would be the two equation in 8.23. Okay, let's see how we can do that. So basically, you want this already separate in the transverse and z direction. So we want to separate that into the same two directions. So let's see what we can do. So grad t. You have grad t cos c. I mean, this is actually a curve. This is a cos product. Right? This is a cos product. So basically, this is a cos product of t, and this operate on that is curl of a scalar plus a vector, and that you can look up the identity. curl of a scalar, which is e sub c called times a vector, but the vector is actually a constant vector z, so it becomes just a gradient of the scalar cos the vector. So a gradient of ez cos in the z. This one operating that ez cos in the z. You can look it up or you can figure that out using the fundamental property of this derivative. It's fast, just look it up, right? And then the only thing different is that whether the direction, you don't want to miss, get the wrong direction, then we get a negative. This causing that, right? T causing z, right? So that's this one, and then there's this e partial passing z and z cos into this. The direction is in z direction, and you cos into the et direction. And the derivative is only on e sub t, so it's z cos into partial e sub t partial z. Right. And finally, it's this one and cos to that one. But this is z direction, this is z direction. So z cos z is 0. So that this will be 0, this operator. So altogether, you have 3 terms. And now you look, you group that into different direction, and to see what the direction is of these things are. So E grad T cos E. So this is like just the X and Y component, right? Just the X and Y component, and ET is also only have the X and Y component. So this cos into that will only involve the Z component. So this one will go into here, right? That is grad T easy. Yeah, grad T easy is only involved in this. But this one is in the Z component, and then this one is grad T of a scalar is in the X and Y direction. Cos in the Z direction is still in the X and Y direction. And so this one is belong to the T direction. And this is Z cos in the T. Likewise, this is actually both are Z cos into something. So this one should be in the transverse direction, right? And that one should be in this direction. Because partial T, partial T, easy. So let's separate and then simplify. So this in the Z direction, so this by 2 equation. The first equation is the C component, which is this equals that one. So because this is in the C component, so only one component, you can take a dot product. So Z dot into grad T cos T. That one. The right hand side is I omega B. That's straightforward. Right? So that should be the second equation of 8.23. See that? That very enough. And then the other equation is the transverse one. Both have a z cos in the sum. So you have z cos into, so you have partial t partial z. And you reverse this direction, becomes minus that t is. And the right hand side is the transverse component I omega t. And the property you want to move the z component to the right hand side. That's because of the next step we'll do. I mean, it doesn't have to be, but just for Jackson, what Jackson did was you want to move this to the other side, and then this one is moving to the left hand side. This one is I omega bt. This is partial t partial c, and this one is z cos. I mean, this one when you move it to the other side, you have the c. You have the z cos into that, and what Jackson writing is just this one. So to get rid of that, you can do a cos product as another cos product. It goes to this becomes z cos into that, right? So when you do another cross product, becomes that you use the triple product rules. The one is in the z direction, and then z dot into the west. But the west is also in the transverse direction. The z dot into this is 0, 0. So the first term is 0 in the triple product. So only the second term, which is z dot into z, which is 1, into this component, but there's a negative sign. The second term is a negative sign. So that's the second term. The first term we already done this one. Then the second term is change the minus sign. So you have minus partial dt partial z. Right, so that is this one, and then this becomes plus grad t z, but we want to move it to the other side. Plus becomes minus grad t z. Or you can put the, multiply by another negative sign. So you move that and multiply another negative sign. So this changes to positive. And move this to the other side, becomes negative, but you multiply the negative sign, becomes positive. It becomes plus I omega c cos omega b. So we got finally get that. So partial e sub t partial c plus I omega z cos bt, right, and equals to grad t z. So that's the first equation of A-Chan theory. Okay, so not too difficult. Right? It's just straightforward separation of this equation into two parts, the following this one, and then separate one equation into two equations. So, these are vector equation. Originally, you have three components, but you group the two transverse components into one equation, which is this equation. And then the rest along the z component is one single equation, which is this. Okay, so basically this is from this is from the Faraday's. All right, then the next step should be a little easier because we can do the same thing for the second equation for the Ampere's law, but without doing that, we can just doing substitution because these two equations are the same form where you see that all you need to transform this to that is or transform this to that is whenever you have E, you change it to B, right? Whenever you have CB, change it to E. Whenever you have I omega, change to minus I omega epsilon. Everything will be the same. So you have the two equations like now. For this equation, you just follow the rule. E change to B. And I omega change to minus I omega minus epsilon mu. And then B changes. And B changes to E. So that's the first equation. A second equation, 8.24. Right? And likewise, this equation change to partial T C minus I omega mu cos T equals to T. Right. So these two are the two equations, 8.24. Right? You have to know what I'm saying, right? To know what I did. But without going through it again, because we already went through it once. This one is basically of the same mathematical structure as this one. So all you need to just do the appropriate substitution, and then you get two more. That's straightforward, right? Okay, and then finally is this two equation, divergence equation, which is straightforward, should be because no, divergence is this one. So that's divergence E. Dot into E T plus E. Okay, and this is a transverse direction, right? So it when you operate in that office, that's fine. It's just everything is a transverse component. But then when this operates in Z, that's the transverse direction doesn't have the Z component, so that dot into that is 0, and then this dot into that is 0 because Z, this is in the C direction, this is in the transverse direction, X and Y, so Z dot either X or Y is 0, and this operator on that is Z dot Z is 1, so Z equals to 0. And you can move this, the second term, to the right, just like what Jackson did. Okay, the partial divergence, transverse divergence of E sub T equals to minus this one, partial E sub C partial C. Right, obviously, likewise, divergence of E is 0. We have two more equations. This 825. Okay, so it's okay. So that straightforward. So these are the Maxwell equations. So we now convert those Maxwell equation into separating the C component and the transverse component. Okay, and now the wave equation is actually easier because you have the gradient. Laplacian is basically Laplacian becomes up transverse Laplacian plus partial C, partial C, partial C, and then plus that operator E or E 0. Okay, so this is the wave equation. And one more simplification is if you consider a single wavelength or single wave vector. So this change to plus or minus I K Z. Right. In this convention, there's a K is all positive, so you have plus and minus. And another way, the way is plus, just plus, and then just let the sign of K determine where you the direction of propagation. Because there's a negative sign for positive omega, and positive C means propagate in the positive Z direction. Negative K means propagate in the negative Z direction. So either way, either you explicitly include a plus or minus in the second term, or just let the sign go into K. That's fine. But this doesn't change this one, because either way, positive Z operate on that. You pull out the IK square. IK square is minus K square. So minus K square. And that is equation 8.19. Okay, so that's even easier than the other equation. All right. So that's all this equation. The next two equations are, we also need some work to get to that. 8.26 A and B. We'll divide that one. Is that okay? But up to here, up to here. So the reason we write this four equation in this form is just to divide the next set of equation 8.26, and the goal is to express the transverse component into the z component. So you want the equation for E sub t and B sub t, D sub t and B sub t, and that in terms of E sub c and B sub c. But right now, this is not exactly this case, because this still involving derivative, and also the, say this, you have E sub t here, B sub t here. They are all mixed up now. A single equation involves E sub t and B sub t, likewise here, B sub t, E sub t. What we want is to just transform this set into a single equation for B sub t. It's basically B sub t equals to something that involves E sub z and B sub c, and likewise for B sub t also. Okay, so we'll do that. Some space, and this should not be very long, but some space to work on the equation. Okay, so we start with the basically, we start with these two equations, this one and that one. Right, and then the rest of the other two equations we'll use that a little later. Okay, at least that we can start see if we can make progress this way. The reason is that we did that for the pain wave also, and hopefully that will work. And so you want to derive the equation of involving E sub t. We want to get rid of B sub t, and one way to do that, because the B sub t here, the second equation B sub t involves the derivative of c, so you can take another derivative of that. Right? You can take another derivative of that, and or you can instead of assuming derivative, you can now make use of this fact that we consider single wavelength, a single wave number, and change all that to all the partial C equation to IK times the partial C becomes IK. Right? And assuming you use this convention, K, the sign of K determines the propagation direction. Okay, so okay, so first rewrite this set of equation. So the first equation becomes IK E sub t plus I omega equals E sub t. The right hand side, grad t of E sub t. Okay, so that's this equation. But this equation is IK E sub t minus omega epsilon plus E sub t. The right hand side is grad t. Okay, so that's even easier than taking z derivative. Okay, so what we can do is substitute this, because we explicitly have a B sub t here. We can put this in on the other side and substitute B sub t in here. I mean, because this involves IK B sub t, so you can, one way to do it is just multiply IK throughout the whole equation. Multiply IK first, and then you have IK B sub t in here, and then you can express that as After you move this term together, to the right hand side plus this one, go into here. That so then you will get the single equation involved. Now they get which of b sub t at least. Okay, so after you multiply ik, the first term becomes minus k squared. Second equation I omega, and then put this to the other side plus this and go into here. So that would be I omega. And mu t, and then plus okay, so that's not too difficult. The only thing now is we want to I mean, we want to solve for e sub t, right? But that one you have the z cos e sub t, so that is a little bit of a problem, right? Because you have k squared e sub t here, and
won't the right hand side also have an angle?
Oh yeah. Okay. One thing we can do to try to get rid of that is doing a cos product with z, right? And to see how it goes. Oh wait, did I miss? I miss a c. Well, that's why I'm struggling. I missed the c cos. Right? Yeah, I missed the c. Why it doesn't work because of that? Okay. So that's the z cos, and I think for this term that's fine. The c cos, and that's not zero because this is in x and y component. C cos in the x and y is still in the x and y component. That's fine. This term you work as a triple product. Again, the z cos e sub t has two terms. The first term is in the z direction, z dot e sub t, which is 0. The second term is z dot z and multiplied by e sub t. Z dot z is 1, but it's a second term, so it's minus. So there's a minus. The second term is also minus, but then you have I times I is also minus, so it becomes plus again. Okay, so altogether the coefficient omega square epsilon mu and multiplied by e sub t, but you already have an e sub t, but multiplied by minus square, minus k square. So altogether is omega square epsilon mu minus k square e sub t equals to the right hand side. Oh no, there's the two terms. This term moves to the other side, right? Because I'm just combining these two terms. I'm combining this one cos into this one. Get to this. I mean this term and this cos into this one going here, and you have still this term. You move that to the right hand side. The original term is ik grad t. The other term is minus I omega Z cos B divided by T. Okay, almost done. So the solve for that is just basically divide whatever the coefficient with the right hand side. So that's, and you have I common factor is just I, and then you have K minus and divided by the denominator. Okay, that should be 8.26a. Let's see if I can. Yeah, that is. We got it correctly. Now the second equation, 8.26b, is from this now, from combining the two equations, this one and that one. Now we could either do it again. I mean, this is basically it's the same, or I mean, there's also something like what we did before by a transformation. I mean, but there's a little bit not trivial, a little bit non-trivial, because if you did that, well, you did this transform to this one, but then you do it again with this one, that one becomes not quite the same. Right? Okay. So, no, I mean, that's another transformation you can figure it out. We could, another way to do it is substitute this into the other part of the equation. I mean, we're working on this. Actually, not this set. We already have that. And one way to do it, substitute this into E sub t. You already have an E. You already have an E sub t. You want the E sub t, right? You want to solve that, right? And then combine this with t, so we can do a z cos into this one, right? And then put it into here, right? We could do that. And finally, we express b sub t, and after substitute this into that, and combine it and divide it by t. Yeah. So let's work up, right? So yeah. So z cos into this first, z cos into b sub t, and now the first term is just z c cos into bracket t easy fine. And z cos into the second one now is again a triple product. And the first term is z dot into this one, which is 0, because we nuclear transform c. The second term is z dot c, which is 1, and in this direction, and minus sign, so that changed to some omega. T. And obviously, you have the same denominator. Okay, so that's not too bad. And now you need to multiply everything and move it to the other side and divide it by k. So we might as well write b sub t equals to 1 of ik. Everything is now on the right hand side. grab T E sub Z, right? And then minus I omega epsilon mu times this one, right? Minus, and you have a denominator. Okay, and then you have I minus I omega epsilon mu, and the rest is this. The rest is this one. You all divided by that, and you have an I here, and you multiply by minus I, which is plus 1. Okay, and then the rest is K cos grad T is omega. Right? Seems like a large term, but then that should be simplification because now we take the common denominator. We have a grad TBC here, and we also have omega square. Did I get the sign correct? Okay. So this one is the sign. The other one you move to the other side, become plus IK. Yeah, that's a plus IK, and then you multiply by I. That one should be a negative sign. Yeah, I forgot that. Right? Because there's a negative sign, move to the right hand side, become plus, and then you have I in terms of I, that becomes negative sign. And the rest is this one divided by the denominator. And multiplied by the rest of this coefficient. Now that's more like it because I want to cancel something. Because once you have the common denominator, you have the omega square epsilon mu times this one. But you already have an omega square times epsilon mu times the same one. So this one will cancel. Only the k squared term. After you do the common denominator out, only the k squared. So actually minus k squared is negative. Okay, and then the rest is this term. So 1 over ik, the common denominator, square epsilon mu minus k squared. And combining the two, you only have k squared minus k squared plus t, right? Because of this multiply that, cancel with that, and the rest is minus omega epsilon mu k z cos graph t z. Okay, so that's not too bad. And final simplification is this minus ik in the denominator. I mean, I'm change I to the numerator become minus I over k. Minus I over k. Minus cancel 1k. So this becomes a positive I times just 1k can cancel the k squared. Right? And then for the second one, minus ik, minus cancel with that. And there's an I, but cancel with the k. Get rid of the k. This becomes positive, and this becomes positive. Get rid of the k. That should be the second equation. So 8.26b. So you have omega square over omega square mu epsilon minus k squared in the denominator. The numerator is there's I forgot this. There's because it's what I 1 over I becomes minus I. I only cancel the sign, but there's still a 9. And then a k grad t bg plus omega mu epsilon c cos the grad t easy. So that's it. So now we finish the derivations. This is the expression for e sub t, and this is the expression of e sub t in terms of e sub c and b sub c. Okay, so the idea is that if we are able to solve for b sub c and or b sub c, e sub c, then we don't need to solve for b sub t and e sub t again from the differential equation, because everything satisfies the same differential equation, right? But solving the differential equation is more difficult, so you want to just solve it one time, so and then or 2 times because you need both e sub c and b sub c, and then once you have that, you don't need to solve for the transverse component from the wave equation. Again, you can just doing by this plug in the formula, doing some derivative, then you can have the expression for e sub t and b sub t this way. Okay, so that basically is saving some steps. Instead of every component you solve them by the differential equation, you just solve for the 2 component b sub c and e sub c. Okay, and there's also a slightly simplification by separate all the wave mode in different kind of classification, and that's what we will do right away. It's okay, but before we do that, the derivation for this 2 is okay. 8.26 is fine. Okay, so